all the elements of group 15 form hydrides of type BiH3, like nitrogen, phosphorus, arsenic, antimony, and bismuth. All the elements form hydride. Like most important are ammonia and phosphine. We just discussed their physical properties as well. Let's discuss some of their properties. Melting points you see, and boiling points in particular. Ammonia got a high boiling point because of hydrogen bonding, but phosphine is considerably low than ammonia. But going from phosphine to further to bismuth hydride, what we saw, there is regular increase in their boiling points. The reason is because of increase in the molecular size. There is an increase in van der Waals forces, which are dependent on molecular size. So that is the reason bismuth hydride having a highest boiling point in all the hydrides of group 15 elements. Next is pH distance. The bond length increases down the group. It means hydrogen atoms are further and further from the central atom as we go from ammonia to bismuth hydride. It also having effect on the bond angle. You see, bond angle reduces because as the bond length increases, bond angle will reduce because repulsion between the bond pairs considerably reduces. Smaller the bond length, more close the atom will be to the central atom, and more closer the proton will be to the central atom, greater will be the repulsion, bond pair repulsions, and larger will be the bond angle. Here we see bond dissociation energy. It reduces down the group. So here we see the correlation between the bond angle and the bond length. As bond length increases, bond angle reduces due to the reduction in bond pair repulsions. Stability of the hydrides decreases from ammonia to bismuth hydride because bond dissociation enthalpy reduces down the group. This affects the two properties of these hydrides known as basicity and reducing nature. So let's discuss one by one. First, from the table we know, as down the group bond length increases, that reduces the bond angle as well as it reduces the bond dissociation energy. So it means down the group it's easy to break the hydrogen from atom of group 15 element. First, basicity. What it is? Capacity to accept protons or donate electrons. This is basic. As the size increases down the group, elements, what happens? The electron density of the lone pair of the s orbital is higher in nitrogen than phosphorus, so on. Their basicity is only because of the lone pair of electrons, but electron density reduces down the group. So basic character, what happens? Because electron density higher means the basic character will be higher. Here is ammonia. So basic character we know reduces with the reduction in the density of lone pair of electrons present on atom. As down the group lone pair electron density reduces because of increase in size. So basicity will follow the same order. Ammonia having higher basicity than bismuth hydride. That's what we get, ammonium ion. Next is reducing capacity. As the bond length reduces down the group, it can easily give up hydride ions. So the reducing character of hydride increases down the group. We know by definition reduction is nothing but either addition of electrons or hydride. So we are having a metal. This is our group 15 element. Hydrogens attached to it. It gives away hydride and attaches to. So what we saw here, bismuth hydride is strongest reducing agent because of weaker bonds. Oxides of group 15 elements. The oxides in the higher oxidation state of the element is more acidic than that of lower oxidation state. So M2O5 will be more acidic than M2O3. The reason is, we know acidity is nothing but addition of electrons. Basicity is donation of electrons. Or the basic character is donation of electrons. So in acidic compounds, because of higher oxidation state, it having a greater tendency to accept electrons than +3 oxidation state. That is the reason they are more acidic than lower oxidation state compounds. These are the oxides of nitrogen, nitric oxide, nitrogen dioxide. There is nitrous oxide, N2O3, N2O4 and N2O5, nitrogen pentaoxide. Predominantly phosphorus show two oxides, P4O6 and P4O10. They got a structure, bridge-like structure. This is a P4O6. What happens here? 4 phosphorus atoms having a intervening oxygen atoms and 2 bridge oxygen atoms. Each phosphorus, when bound to another oxygen through double bonds, it forms P4O10. It is a simple thing to remember. Oxides of arsenic and antimony are amphoteric in nature. These oxides are acidic, nitrogen oxides are acidic. Arsenic and antimony are amphoteric, mean they can show both acidic as well as basic behavior. While bismuth, they are predominantly basic. If you remember correctly, the metallic oxides are basic in nature, non-metallic oxides are acidic in nature. And metalloids, they are amphoteric. All these stable halide compounds of nitrogen is NF3. So only stable halide is NF3 for nitrogen. Another property, pentahalides are more covalent than trihalides. So pentahalide compounds are more covalent in nature due to their higher positive oxidation state of the central atom. These atoms got a strong polarizing power. Due to their strong polarizing compared to trihalide, they are more covalent according to Fajan rule. If you remember Fajan rule, smaller the size of cation, larger the charge on cation, it will be more the covalent compound character it will have, larger the size of anion, it will having a better covalent character. So for this reason, it having a higher charge, it makes a covalent compound. Now reaction of group 15 elements with metals. These elements react with metals to form their binary compounds, and they show -3 oxidation character, because -3 oxidation state is because these elements are more electronegative than our metals like calcium, sodium and zinc. Calcium makes a calcium nitride, calcium phosphide, sodium arsenide, zinc antimonide, magnesium bismuthide. These are the binary compounds. Through reaction of our group 15 elements with metals like calcium nitride, when we react calcium phosphate with the carbon, we getting a calcium phosphide and carbon monoxide goes out. Calcium phosphide acts as a rodenticide. How? If you dissolve this, when the rodents will eat calcium phosphide contaminated food, what happens? Calcium phosphide in the digestive tracts of rodents decomposes into phosphine and calcium hydroxide. The phosphine gas is poisonous and kills those rodents. Now, let's talk about dinitrogen. Commercially, dinitrogen is produced by the liquefaction and fractional distillation from air. First, we compress our air to get a mixture of liquid nitrogen and liquid oxygen. Then further we'll take it through a fractional distillation and getting liquid nitrogen. Here boiling point of liquid nitrogen is 77 Kelvin roughly, while of oxygen is 90 Kelvin, so it is having a higher boiling point. That's how we'll get it. We'll get liquid nitrogen. In lab, we can get a dinitrogen through first reaction of ammonium chloride with sodium nitrite. We having a nitrogen gas coming out and conversion of water and sodium chloride. Remember, sodium chloride is a salt, so it is non-volatile. Nitrogen is a gas, it immediately comes out, and water, it can come out as a vapors. To get a dry nitrogen, what we'll do, we'll pass the exhaust of this chemical reaction, the output of this chemical reaction through a silica cake or silica beads. Silica will absorb moisture and we're getting dry nitrogen in lab. Another reaction is ammonium dichromate decomposition. We heat it up, this compound. What happens? We are getting a nitrogen, water and chromium oxide. This dichromium oxide is a stable compound. It settles, and by passing through again silica gel, what happens? Silica will absorb the moisture, and nitrogen comes as a dry. It can be used. Another decomposition is barium nitride. If we heat it up, we are getting a barium as well as nitrogen. This is another way to prepare nitrogen in lab. On commercial scale, we use dinitrogen to manufacture ammonia. The process of manufacturing ammonia from nitrogen and hydrogen is known as Haber's process. It is one of the most important commercial process because of the great importance of ammonia in chemical manufacturing. So first we introduce nitrogen and hydrogen gases to a system. we compress these gases to very high pressures using compressors. These highly compressed gases then passed through a catalytic chamber having iron oxide, alumina, and we having a potassium superoxide, K2O, potassium oxides. So, in the catalytic chamber, nitrogen and hydrogen reacts to give us a mixture of nitrogen, hydrogen, and ammonia. We are getting a mixture. From it, this mixture, ammonia is extracted, liquid ammonia is extracted, and rest of nitrogen and hydrogen is pumped back for the catalytic chamber. This is a simple diagram for ammonia manufacturing through Haber process. As you know, Leach-Atelier principle. With high pressure, the reaction moves forward because of reduction here in the number of molecules produced. So Leach-Atelier principle is used for manufacturing of ammonia. Applications of liquid nitrogen. It is globally used as a good refrigerant to preserve biological samples. All semen samples are preserved in liquid nitrogen. Whatever today's stem cell preservation techniques, they use liquid nitrogen for preservation.